is do a quick repeat of the last part of Tuesday's lecture on clustering using core sets. The idea will be sort of just to reinforce, I felt like I went through it a little bit quickly last time. I want to reinforce what we talked about in terms of how you can think about clustering using core sets. And then I want to build this up into a technique to actually do clustering on a string. Now, and the reason, of course, is because we're talking about how to do clustering at scale. And we're doing clustering at scale, as we saw last time. Many of the clustering algorithms we work with have expensive running times in terms of the number of points in the input or the number of dimensions. And these are just completely impractical when you have a lot of points. So there's a whole, I think, universe of tools that are out there for doing data analysis at scale. It's a very fascinating topic, and it's a topic that we can't really cover in any great deal of depth in this class. There are other classes which we talk about this more. But roughly speaking, there are a few different ways in which you approach the problem of large data X, whatever X may be, in this case X being clustering. You either try to sample to reduce data size in some form, and we talked about ways in which you might try to do that and what those problems might be. You somehow say, well, I'm going to look at the data, but I won't look at it very much. I'm going to just do one pass over it. And there's also things where you can do things in a distributed setting. You have different nodes have different parts of data, and you somehow want to combine them in some way. So we'll try to talk about all of these things. And today we're just going to continue with this idea of using core sets, which, to refresh your memory, so the idea of a core set again is to say, right, so given some set of points, let's say P, and some task F, you can think of F as some function from the 2 to the R to the D. So sets of points to some number, right? So some kind of score function, the quality of your clustering or what have you. And the goal is that you want to find some S subset P. There are variants where S is not a subset of P. These are called weak core sets, but I'm not going to get into that now. Such that S is much less in size than P, but F of S is relatively close to F. The idea being that you want some small representative of the data, very small, so that the representative tells you what you want to know about the data. But because it's small, the running time of your problem, let's say instead of taking time G of P, which could be very large, it basically takes, instead it goes to something like the size of P plus G, the original algorithm run on S, which is one small. So this hope is that going from here to here, you win. And of course, the higher the polynomial this is, the more you're going to work. Right? Because this is going to, hopefully it's going to be reduced by a huge amount. And we saw an example of where you can actually do such a thing. We looked at the problem of one center, right, which is a minimum closing ball. So it's a clustering problem, but a very simple one, where we saw that you can get this set S, and S has size, at least we showed in the class, has size something like some 1 over epsilon squared, such that the MEV of S was greater than or equal to 1 minus epsilon times the MEV of P. And there was an algorithm that could compute S to take some time. I mean, the algorithm basically said, take a point. If it lies significantly outside the minimum closing ball of the points you've seen so far, add it in. Otherwise, throw it out. And so when you say significantly outside, the idea was you maintain some kind of ball around the points you've seen so far. If the new point comes in, if it's really far away, more than 1 plus epsilon times the ball radius to get it, then get it, because it's interesting in some form. And if not, put it in. And I gave a brief sketch of how you prove that after these many steps, the ball you get is going to be reasonably large in size. Roughly that the radii increase fast enough that after these many steps you're at. Okay? So this was a proof of concept, a claim that, in fact, there existed a set of small size that could do the job for you, that there was some hope of finding core sets for a problem. Right? And that if you then could compute the set, you could throw away the original points if you wish and work only with this. And that's the modularity is an important aspect of this. What I want to do is treat the set like the input, and therefore I want to run the same algorithm I would have run before on the data on this set. I don't want to do anything different. Right? You could indeed imagine that I would take this data and then do something different on it to get some number, and that number would approximate the minimum closing ball well. And that would be fine. But that's not what I want to do here. I want to make the algorithm kind of blind. You know, all that changes is the kind of inputs I plug into it. And this is going to be important in what we see now, because this blindness is going to carry on across multiple levels. Okay? So are there any questions about sort of this quick review from last time before I move on? This is all kind of, well, remember, does this make sense? Okay. So what we talked about last time, again after this, was to say, if you had to generalize this to a clustering problem, more than just a one center, right? It's not clear how you compute this. This algorithm, we said, find a point and build a clustering and see if there's something that's far outside of it. The way you try to generalize this to clustering, obviously I take k points, then every new point that comes in, you add it to a current ball if it's significantly far outside the ball for that. And it's not, now that I say this, I think, okay, maybe there's an algorithm you could prove something about here, but I'm not sure you can. I don't know yet. That's an interesting question. So I don't know yet if there's a way to show that that kind of simple idea would give you any kind of bound for a core set for k-center clustering. The actual algorithms that do work for k-center clustering are a bit more involved. You kind of find one of these things, peel it off, and do a lot more work. They're kind of grungy. Okay, anyway, that's something to think about. But what we will do is come up with a different idea, which exploits yet another property of core sets. Roughly speaking, that if you take two core sets and put them together and you compute a core set of that, that's equivalent in some ways to compute a core set of the original. So let me be more precise about this. So let's say I have two sets of data. So I have P1 and I have P2. What I'd like to do is compute a core set of P1 union P2. So let's call this some S. Okay. What I instead can do is compute a core set of P1, we'll call it S1, compute a core set of P2, we'll call it S2, and compute a core set of these two sets. Remember, they are also sets of points. So if I had some blind algorithm to compute core sets, I could just give it these two sets to begin with, and these are very small. Right? And let's call this S prime. The crux of what we're going to talk about is the following fact that for many reasonable course problems, this core set is going to be very similar to this core set in terms of what it tells you about the data. So in some sense, it means there's a kind of a divide and conquer method baked into this whole process. That it allows you to split the data up into small pieces and then put them back together later. And that's going to be very, as you hopefully already have seen before in other kinds of large data problems, the ability to split things up and then put them back together later is very powerful. All right. So what does that mean? So this kind of we'll call it the the merge problem. That basically S is roughly the same as S. And again, this is roughly, right? So it's not quite, it's good enough. Okay. So let's take a concrete example of this. We talked about thinking of points in the plane, and we said, okay, so I have my points on the plane scattered in some various positions. And then I'm going to build a grid on my data. And then what I'm going to do is I'm going to snap all the points to their cluster set, to the centers of the grid cells. So this is a grid cell. And then we said, okay, we'll just snap all points. And so we'll say this is my point in my new set, and its weight is 1. This is weight 1. This is weight 2, 1, 1, 1. It's a very boring course I put in. 2, 1, 1, and then 1. And my output is just these points with the weights attached to them. So my output consists of Pi and W. Right? It's a weighted point set. But it's a small point set, because hopefully, the way I built my grid, maybe if I built my grid the right size, I have lots of points inside each blob.
So
yeah.
we're in the plane, in Rn.
In the plane, we're in R2.
So this PIVI can be constructed in ON, right? ON times D.
Yeah. It's very easy to compute this thing, right? Exactly. Yeah, because you can think of the grid canonical. You don't have to build it per se. You just think of it canonical.
Yeah,
so you just round every. So n times D is enough.
Yeah.
You just round every coordinate you get done. So this is not hard to compute even in D dimensions. And so now we can say that if we think of this as sort of, we'll call this, so for any point Pi, we'll let Pi hat be the grid cell that it corresponds to, right? So in other words, if this is P5, its P hat 5 would be this grid cell here. Okay? And now we say, okay, now that we have a new data set, we're going to run our clustering algorithm from before that we had, some magic clustering algorithm, on this reduced data set. And we want to know what the error is going to be. Right? And so what we said was that if you look at the cost of clustering the PI hat, right? Yes.
So what's a good way of choosing the width of the square?
That's good. It's a good question. Right? There's a trade-off. If you make the grid cells small, okay. Let me actually finish writing this function. Then I'll answer your question because it's going to exactly answer the point you're trying to make. So you write down this function, and the cost of this, right, can be decomposed into two parts, right? So so think of the clustering you get from clustering these PI hats, right? And for each PI hat, there's a corresponding original point PI. So in other words, in this world, in the world of the grid, some point PI is going to some cluster C hat J. When I'm bringing the hat to say it's all happening in the grid land, right? Some P hat I is it. But of course, this P hat I came from some actual point I, which maybe should have gone to some actual cluster CK in the real clustering, if you have the optimal clustering, right? What we'd like to do is relate this cost to this cost. And by triangle inequality, you can say that if I instead assign these points here, you can rewrite that cost as this to this plus this to this, right? So in some sense, the cost of assigning these grid points to the true clustering, okay, is at most this plus this plus this. So it's basically less than or equal to we'll call this number R plus the cost of assigning the PIs to the true CIs, which is let's call it opt. Okay. And so since we're going to have some actual clustering we compute, right? That's if we had the optimal clustering, it's going to be like this, or going to be even better than this. Right? It can't be worse than this, the optimal clustering, because there exists a way to cluster these points into clusters to have this cost. Right? So if I do some actual clustering on the grid points, I'm going to get some actual answer. But if I look at the best possible answer, it's going to look like this. It's going to have this property. So that's what we've written here. Because this is a particular clustering, and the optimal one is below that. Opt hat is less than that. And what is this term? This term is basically, and I should have mentioned the cost function we're using here is the K median cost. So you're adding up all these things, this makes it simpler. So it's going to be sigma over all I, the distance from PI to PI. Now this brings me to the answer to your question. Right? If you make the grid cells very small, then the error in snapping a point to its grid cell is going to be very small. And this number is going to be very small. So we're happy. But we also get very sad. And why is that?
We have lots of P's.
We have lots of points. You haven't really done much, right? I mean, in the limit, your grid cell size is so small, you have one grid cell for every single point. You benefited nothing.
Yeah, but what I really wanted to ask is, like, how do you know in advance, before you run this? Yeah.
You don't.
Yeah.
And that's why I'm not going to use this algorithm at all.
Yeah, so
This is merely an intuition to motivate what you really want to do.
Yeah.
This is merely an illustrative example. Maybe it's not as illustrative as I would like it to be, but it's an attempt at an illustrative example to motivate what we really want to be doing here. Okay? So don't worry. We're not actually going to do this in the grid. Although there are some clustering algorithms that work this way, we're not going to do this. It's going to give you some intuition, right? And so the trade-off between the grid cell size and what you do is that essentially either you make this number very small, in which case the size of your S gets very big, or you take these gigantic grid cells and everything collapses to one point, so you're happy about that, but now your error goes up by a huge amount. But there's some trade-off. But the point remains that if you could do this, then you get this relationship here. That you can relate the optimal clustering on the modified data to the optimal clustering on the true data, which is the real game we're trying to play here with this property. Okay? And the next thing to realize is that there's nothing special about the grid. All we're using here is that we have triangle inequality that gives us this expression, and that eventually we can bound this using the grid. But if we had another way to bound this property here, we wouldn't need the grid. We could use any method to collapse points into groups, and that would give us an estimate for this. And the insight is that we already know how to collapse points into groups. That's called clustering. The whole point of doing clustering is to collapse points into groups. So one way to cluster the data is to cluster the data, get these groups, and then cluster the group centers. Which of course doesn't make any sense, as I said last time, because now you made this whole thing circular. But every circular reasoning is the birth of a recursive algorithm. That's something you should keep in mind. The best way to design a recursive algorithm is to design an algorithm that's circular. But then within that circularity, you just make the things get smaller and smaller and smaller. And lo and behold, you have a nice recursive algorithm. And that's exactly what's going to happen here. The snake that's eating his tail is actually going to eat a smaller version of its tail each time. So eating its tail. So what's going to happen? So what we said was the algorithm to cluster the data. So cluster P, step 1 is cluster P, right? Step 2 is cluster the centers. So this gives you centers C1 through CK and weights W1 through WK, cluster the centers, right? How would we make this into an algorithm that actually can be implemented? So the trick here is that we don't actually have to cluster P extremely well. We can do something very crude, right? We didn't say how we should cluster P. In fact, no matter how we do this relationship is going to be true. Okay. Furthermore, notice that this number is the cost of clustering, which is at most this. So if you had a good clustering algorithm to do this, then this cost in the modified space is at most twice as much as the cost in the original space.
The good thing is that we don't need to specify K.
Exactly.
In
the first step.
Yeah.
Exactly.
Because we can just, we can say, okay, we're gonna group points if they're that close.
Yeah, we're just gonna do whatever.
And then you just run, just group them.
Yeah.
In, let's say, this RD space.
Yeah.
And then you run the
exactly. And that's the crux.
And then you have complete control over R.
Yes. And the crux of this entire argument is exactly that. That this first step can be done very crudely without thinking too much about it. Because all you want to do is get some rough grouping. Because this argument is very flexible. It doesn't care how you do the grouping, as long as you have some control over the error in this grouping process. But the error in this grouping process is in fact your clustering cost. So this number is basically opt. So this number is basically less than equal to 2 times opt. So as long as you have some procedure for dividing things up and putting them together and back again, like we said here, you will only incur a factor of 2 in this process. I say only, but whatever. You can at least put some form. So the idea here is going to be to replace this step, right, by something else. It's going to say instead, divide P into say, I don't know, L groups. Okay? In cluster each group. I get something like K clusters, but I don't really care. So let's say I have O of K clusters. Okay? So if I do that for each group, I'll have something like O of L times K centers here. So I'm going to cluster the O of L times K centers. Okay? So notice that I can now split up my jobs nicely. Each group can be clustered separately, or I can do it one at a time. Right? So the amount of space I need to deal with this is roughly N over L plus L times K. I have to store the LK clusters eventually to do something with them. But for any group, I only need to spend N over L space. So if I make L large enough, I can be, I'm in business here. So in particular, you could make L something like square root of N over K. This would balance the root term or something. Not saying you should do that, but you could. Yeah.
When you said divide P into L groups, you
Yeah.
didn't mean like actual groups. You just meant like samples.
Not samples, partitioned. Partition P into L pieces.
Yeah, but those partitions, they don't have like some kind of
Nice structure.
class. Yeah.
No, No,
Just
arbitrary.
arbitrary,
Arbitrary. You can
yes.
take the first L, the first N over L, the next, yeah, exactly. So, yeah, you could randomly do it if you want.
That's-
Yeah, arbitrary, yeah. Any way you want. Okay? And because of the property we said here, if you've done everything perfectly here, you will get a 2 approximation. But of course, we can't do this perfectly. This is going to be approximate as well. So you get some extra approximation from there. Whatever approximation you have for your low-level clustering algorithm, you'll pay for here. Okay? So this is kind of this what we call the clusters, the paradigm. And it's a very pervasive paradigm in this area.
And what is the center of the property?
The center, so when you take each group and you cluster it, you get some k clusters, and take the average, take the centroid of each of them. Whatever your clustering algorithm gave you, it gave you some centers, and then those are new points. So it's a good point that you have to have a clustering algorithm that gives you centers. A clustering algorithm just gives you a partition is not good enough. Like we've seen methods just gives you a partition of the data. You want one that gives you actual centers, and then use those. So if it was k-means, you would have a centroid. If it was k-median, you'd have whatever center represented. Okay.
What's the motivation for the first step? Divide into L arbitrary partitions.
The motivation is that you can play this game with space. You can reduce space requirements for your method. And the next motivation is coming up in a second. I want to stop before we go on, but you'll see how it comes up. So does this make sense to all of you? That using this idea that is built from the grid. That's why I said the grid wasn't very important, because the grid just gives you the intuition for why this should work. But now I'm saying take away the grid and replace it by an arbitrary clustering algorithm. But one that's kind of crude. It just does kind of a very crude job, but that's enough. And all you need for all of this to work is a triangle inequality. So again, I've said that it's important to understand what properties of the space we need to make this work. All you need is triangle inequality. Now, if you want to do things with centroids and k-means, of course, you'll add extra structure to your problem. You'll have vector spaces. But for this, you don't need anything else. So it's quite general. Okay. And now the fun part comes in. Because if you look at step 1 very carefully, right? Actually, look at step 2 very carefully. Step 2 is saying this, right? We need an algorithm to do that. What's stopping us from using this algorithm again to do this? Nothing really. In fact, the essence of a good recursive strategy is to just keep applying it over and over again.
Just need to define the basis.
Huh? Just need to find the basics, right, exactly. So once you have that observation that to cluster these centers, I could use the same algorithm over again, what you end up with is a hierarchical algorithm. Right? So you end up with an algorithm that looks something like this. You take your data set, you divide into groups. Right? Each group gives you a few centers. That's your next group. Now you divide them into groups. That gives you a few more centers with the parameters appropriately chosen, and so on. Till you get one group and you find clusterings of this, and this gives you the final cluster centers. Notice that at every step of the way, you're going to lose a factor of 2. Right? So if you have L levels, or not L, let's call it let's say T levels, then the total error you're going to pay is going to be something like 2 to the T, which is not great, but just keep it in mind. So as long as the number of levels you use aren't too many, this is an okay. So hopefully you see this, that once I have, so what we've done, what we said, we start with the simple idea of doing a clustering followed by a clustering. That gives us this method, which we can give a 2 approximation for. And now we apply this truly recursively to get a hierarchical approach. And again, so far we haven't done anything much yet. We're still working with a method that has just a divide and conquer based approach. But it has this property that you can now, in a parallel sense, you could imagine distributing these locally and then moving them up, and all of these nodes communicate just their cluster centers to this and so on.
Where is it 2 there? It's not.
You
You need to relate the n points to L times k.
Yes.
Is that the factor of 2? Did we
No,
choose?
no. I didn't say the size of factor of 2. I'm saying that every time you do with one step of this approximation, you lose a factor of 2 in your error.
Oh, okay.
So the amount of error you're going to pay is going to double each time. The complexity of this you can
Yeah,
analyze.
but you can control the depth. basically.
Yes, you can control the depth. You can just do one level.
Yeah.
Yeah. But the more depth you have, in some sense, the smaller these groups need to be. Right? The less depth you have, the bigger these groups need to be. And so there's a bit of a trade-off there.
Sure.
Okay. So the final piece of the puzzle that gets us something that's actually interesting is to make a final observation. So suppose you want to do this as a stream. Okay. How many of you are familiar with streaming algorithms? Hands up. About half. Okay. So let me do a fairly quick rundown of what a streaming algorithm is, because it's kind of an interesting object that comes up a lot in large data problems. So as we know that, if you have data, for example, sitting on disk, you don't want to keep pinging your disk sort of over and over and over again because it's very expensive. You'd like to be able to kind of scan the data in one pass and do something with it. A streaming algorithm is a logical the limit of this idea. It says that the only way, so what's going to happen, your algorithm is allowed to do only the following. You have your machine here. You can think of it as kind of reading a long tape. Okay? The data comes in one by one. It streams past your machine, which basically means that the item comes in, you can look at it, you can do something about it, and then it's gone. So then you can say, well, oh, fine, I'll just copy every item into my local store when I see it. There's a catch. The streaming algorithm does have a local store, but it's very small. In particular, if this stream length is n, if you have n objects, the size of your memory has to be smaller of n, which means strictly less than n. Right? Maybe square root n or polylogarithmic n or whatever. And so you have to now design an algorithm that, in some sense, is an amnesiac. Right? It has very bad long-term memory. It can't remember things. But even though it can't remember stuff, you hope that it can remember enough information about the data so that it can do something with it. And the reason why this model is interesting here is because it's become a very powerful and successful model in thinking about how to deal with lots of data. That if you can design a streaming algorithm on your data, if you think about it now, what's it doing? It does one pass over the data and it's done. If you're able to compute whatever you can, then it's going to be efficient by design because you don't do anything with the data at all. If your data is sitting on disk, you scan it once. If your data is actually coming off a network stream, you're just looking at it once. So if you want to design an algorithm that works efficiently in scale, this is one way to do it. There are others, but this is one of the most popular ones. So when we're talking about large data clustering, a natural question is asked, well, how do you make a streaming clustering algorithm? And this has been a topic of great interest over the last 5-6 years, so there's been a lot of nice work on this. And it turns out that this idea of clustering the clusters is a very powerful way to design a streaming. In other words, if you want to design a streaming algorithm for a problem, you could in fact say, forget the streaming part. Let me design some kind of recursive strategy, make this hierarchical, and there's almost an automatic way to convert that into a streaming algorithm, which is kind of neat. And the question is how you go about doing it. So what we want to do is take this idea and make it streaming, with the proviso that we're not allowed to spend too much space. Okay?
And we can get any point.
Yeah, the data can come in arbitrary order.
And we can
usually.
get any point in our space. Like outliers.
Oh yeah, we can do it. Yeah. We're not worried about outliers for now. We're assuming the cost function takes care of that problem, and if it doesn't, that's a different story over here.
Aha.
But we're not worried about outliers right now.
So then we can just simply say we have that many clusters. Let's say K. Then we put the points in. The first K points, we put them separately. Yeah, separately. And then the next point comes in, and then we assign it to the closest one. But if it's, if they are too far apart, we join two and put that one separate. And we repeat this process. This process works if you have sort of K clusters and you have outliers, otherwise you're going to start merging all the time.
Yeah, so now what do you do?
When you merge?
No, I'm saying if
Oh,
your data is arbitrary, it could be, and it could become also an arbitrary order. But what I want to do, I mean, I already have a template for what I want to do. I just want to somehow implement this. I mean, it's an easier problem. I don't have to implement an arbitrary method. I want to implement this method.
So we don't have any, like, the items come, or you can stop them and do some computation and then get rid of them and then take the other.
Sure. So you can assume that, yeah, the speed at which they come is not an issue. Yeah. So you're allowed, within reason, to stop the stream to some. If your computation takes, exponential time, then I would be very happy with you. But you're allowed within reason to stop, do something, and then continue.
So time is not important.
For the classic streaming algorithms, it's usually the streaming algorithms don't actually have bad running time, so it's okay. But you are allowed technically to abuse the model, because I'm not charging you for the amount of time. It's like verification stuff. I'll use the model in many ways. So yeah, so you are allowed to do that, but let's try not to. Let's try to be sort of well behaved in that respect.
Well, if you have such a tree, then you can just traverse and put it where it goes, right?
Yeah, but
the
I can't
question
store
is,
the entire tree,
how do they come up with the tree?
and I can't store the entire tree either, right? I mean, that's too expensive.
No, you cannot store the leaves, but
Yeah.
you can store to a certain time.
But if I store everything, say up to one level below, then that's almost as large as the entire input.
Twice as, yeah.
So, but it's a smaller.
Yeah.
So think of the following idea, right? So think of trying to construct this tree, knowing that you want to construct a tree, but imagine sort of data coming into one side of it, right? So what's going to happen, right? So imagine this hierarchy in your head somewhere, right? That you imagine that this is how I need things to be. So you know that the first, some number of items are going to go into this, right? And the next some number of items are going to go into this, and then go into this, and go into this, and so on, right? Okay. What's going to happen to the items that go into this bin here? What are you going to do with them at the next level of the hierarchy? You're going to cluster them, right? You're going to cluster them and put them up there somewhere, right? So in some sense, you can fill up the first, blah items here. As soon as you get that many items, cluster them. That gives you a smaller set one level higher. And the next set of items comes in, fills in the next bucket here. Okay? Now the next set of items fills in, right? And it's going to fill in, and when you get enough of them, you're going to cluster this, right? So now the same problem at this level. I don't want to have to maintain all these things. But once I have these two, what do I know I have to do with them? I have to cluster them immediately as soon as I get them. So now I get a third level. So at any point in time, you could imagine the stream algorithm essentially implementing some part of the whole computation here based on how much data it's seen already. Because the partitioning is arbitrary, right? I could just say the first X number of items in the first bucket, the second X number of items in this bucket, and so on like that. So if you look at what the stream algorithm is doing, essentially it is maintaining some sort of branch of the entire computation. Right? It never needs to maintain more than a branch plus one extra thing hanging off, because the minute it gets two extra things hanging off, they get merged. Right? And the space to store that is much less. Okay. So this is kind of a weird thing, right? I mean, if you haven't seen it before, it just seems very strange. That you're processing all the levels of the hierarchical recursive algorithm simultaneously, knowing that they have to happen in a certain order. Leveraging the fact that you know exactly what order the points come in, and it doesn't matter how you partition them at the lowest level. And this trick is very, very powerful. Like I said, it applies to any problem where you can formulate it recursively in this manner. If you can take the problem and formulate it recursively, and then build this tree, you can make a streaming algorithm from it. And there are many streaming algorithms that come from it. Right?
Can it happen that when you add a point, you need to do many clusters?
Yes, but that's a time issue.
Yeah, that's what I'm
Right,
saying.
and so it depends on the height of your tree.
Yeah.
So it's okay. As long as you manage the height of your tree, you're going to be fine. Yeah, the height of the tree is not going to be that much.
Because it can happen that you would need to compute.
Yes, absolutely. So you have like a domino effect. This merges that, merges. Okay, so what does this mean? What this means is that and so this is an example of one particular streaming algorithm for the K-mean. So this gives you sort of the first, so this was about, I think, 10 years ago. This was the first algorithm we had that had a provable guarantee for doing clustering in a stream. So it gave you a streaming K-mean algorithm. And the parameters here that you needed were something like, so remember that if you reduce the size by a certain fraction every step, so let's think about this for a second, right? So, so what I want to say is, if you have a certain size at the base level, what level is it going to be? So we know that if you have, let's say, S nodes at the base, and you sort of merge them up pair by pair, the number of levels in the tree you're going to need is something like log S, right? So let's do a little thought experiment. If you had so let's see. So if you have two groups, you get one thing here. So you have each of size n over 2, right? And then you merge them up top, you get an answer there. If you have n over 4, you do two levels here, 2 levels here, 2 levels here, and you get, so this gives you an error 2, this gives you an error 4, and again, you put it there, and the amount of space you need is this, is 4 times the size of each individual bucket here. So what I'm trying to get at is that what you want here is something like number of levels is something like 1 over epsilon for some error term epsilon. And this should give you that the size, the amount of space you need to store any individual thing. I mean, you need to store the individual thing here. So the amount of space you're going to need is going to be something like n to the epsilon. You have to store one blob for each of these things, so or maybe 1 over epsilon times that. And the error you're going to pay is going to be 2 to the 1 over epsilon, which is again large, but it's still constant. So again, if you think of epsilon as say half, number of levels would be 2. You need square root n things because so right. So let's take the case when epsilon is equal to half. So this is saying you need 2 levels. This should be square root n, and this should be 4. And the reason that's going to look like that is because you're going to have blobs of size square root n. So there'll be square root n such blobs, right? Each blob will give you some constant number of centers of O of k centers, right? So then you'll have something like square root n times k points, and then you're allowed to run a clustering algorithm on square root n points. So that gives you one more thing there, and that gives you the one up top. The total space you need is going to be this much. Each blob is of size square root n, these 2 blobs. So that's the space one you're going to have. And then the error is going to be 4 because you done this merge 2 times. That's not okay. Okay. I might be off by 1 here. That doesn't matter too much. Okay. And if you have, if epsilon, if you're allowed to use more levels, you can make these things even smaller. Right? And obviously, the smaller you make it, the better you can do on each individual piece, but then you pay error terms. Okay. So this was the first streaming algorithm for the K-median problem. Let you do this. And the important kind of highlights you want to remember from this, right, as a design strategy, is that you can break things into pieces and then merge the pieces together, treating the cluster centers and the pieces as first-class objects. That is okay to do. You get a good answer from that. And secondly, what's interesting here is that even if you want k centers at the end of your algorithm, you don't have to use k centers in the intermediate steps. You can use many, many more centers, in fact. Okay. So one problem with this method when it first came out was that you need this much space, but your error was pretty bad. And the question was, could you do better? Could you get this constant error but not pay too much space? If you want to get, if you want this to be a constant, this space is going to be some function power of n. In the streaming algorithm, I generally am happy if my space is some log n to the c, some power of log n. I'm not as happy if it's square root n or n to the 1/3. I'll live with it, but I'm not that happy about it. And so the question was, can you keep this error constant while still keeping this logarithmic? Because in this algorithm, you can't do that. So it turns out you can. And again, I won't go into detail, but the algorithm is more or less the same thing. That you use that same trick, but you cluster in each piece, in each sub-piece, you cluster into something like k log n clusters. So you actually cluster into many, many more clusters than you actually need. Okay, so you have this built-in redundancy in the intermediate steps of your merge process. And at the end, you clean everything up and get k clusters. Okay, I won't go through the analysis here. It's much more involved. But then you can actually get polylogarithmic space and constant error. And again, the importance here is to emphasize this point, that when you're doing this hierarchical clustering in this manner, by dividing your data, don't worry too much about having the right clustering in each individual node. This is intuitively reasonable because each node doesn't have the full picture. So you shouldn't try to optimize it too much. And it's okay to be very sloppy with it, and that's enough. You be very sloppy locally and merge them at the end, do a cleanup phase. And it turns out that a very large number of heuristics for doing streaming clustering that existed well before this method, in fact, that motivated this method, use essentially that idea. Okay? That they all use this idea of somehow building this hierarchical structure, computing rough representatives and merging them together and then doing something. Might end early today. And I want to give you one example of such a method, because it's a method that actually been used a lot in practice. It's very popular. It's a heuristic. And in fact, these methods were designed in response to that. But as you've seen with clustering, this is constant, here's a heuristic, here's analysis, and they'll actually look quite similar. Now you know that there's a formal reason behind why these methods work. So this method is called Birch. This is a very old paper. It came out something like 20 years ago. But it still, has been very successful as a method for doing clustering. There are other methods now based on how to implement this, say, in MapReduce and all that are basically the same idea. So I'm not actually going to them in any great detail. And as long as you remember this basic trick of clustering the clusters, you'll be able to see how they work. But I want to talk about Birch because it was one of the first ones that was very popular. So if you didn't know anything about streaming, you didn't know anything about clustering and clusters, what would you try to do? And Birch is kind of the result of that. It was kind of a nice idea. And the idea was that what you wanted to do was maintain subsets of the data with short descriptors. So in other words, you had some data, so you had some points at P, you partition P into P1 up to P R, some large number of sets, and for each set, you maintain some kind of description of PR. With the property that the description of P union P prime should be expressible in some form as a description of P combined in some way with the description of P prime. It could just be that you add two things up or you combine them some clever way. This is the same trick we're using here, right? We're saying that a core set of the entire set can be computed by computing core sets for individual pieces and putting them together in some way, right? And this is, again, a very, very important idea when doing large-scale data analysis. You really want to build things that have this property. Because then this works, this works, this works, everything starts working for you. And so this idea of sketching, some of you are in the class that Jeff and Meena are running on matrix sketching, uses, again, the same idea. that you build these sketches that are linear. Right? And linear means that the sketch of the union is the sum of the sketches of the individual things. Right? So you can think of this as a proto-sketch from back before when people were even talking about sketches. This is like an initial idea of a sketch. And of course now we have much more sophisticated ways of thinking about sketches. But the core idea of linearity and linearity leading to hierarchy, hierarchy leading to streaming just keeps working. So it's kind of cool that way. If you just have this one little thing you can design, then the whole machinery kind of kicks into gear and you get an album. And what was the descriptors that were used here? They're very simple descriptors. So descriptor of point set was basically three things. It was a vector consisting of the number of points in the set, the median, the mean, sorry, and the variance. So the sum of square distances. So for each group of points, you maintain these three things. So of course this was, this is a single number, this is a collection of d numbers, and this is another number. So basically it's a d plus 2 coordinate representation. Okay. So that's a single blob, a single vector for each thing. And it's not hard to see that if you have the representative, so these are called CF vectors. And it's not hard to see that you get the CF vector for one and the CF vector for the other. You compute the CF vector for the entire thing. Right? Fairly easy. Just by taking this one. And that was basically how the algorithm would work. So the algorithm works very much like these algorithms are working. You will get your data coming in. You take your first collection of data, you build a CF vector on that. You take the next collection of data coming in, you build a CF vector on that, so on. And then you merge them up to get a new CF vector and a new CF vector. The difference in Birch was that Birch was not designed for streaming. It assumed you had the whole data. And so what it would do is it would say at the leaf nodes, right, you make sure, and going back to our picture here, so if you have a bunch of points in space here, make sure the leaf nodes in some threshold where things that are close are put together. So you start off with clusters that are kind of reasonable. You don't start off with points that are all over the place. So now streaming algorithm, that could have happened, we didn't care. But for things like Birch, you need to make sure, and this was not streaming, so you could do this, make sure you start off with blobs that are reasonable. In other words, that this distance was less than equal to some threshold t. You put some parameter on your system. So you start off with the leaves and build CF vectors for those things, and you build them all the way up to the top. And once you build them all the way up to the top, it's very easy to do clustering data, because now you have a nice representation of your data, and you can cluster it very nicely. And so, like I said, Birch was one of the most, it got a Test of Time award a couple of years ago and all. It's been a very popular tool. And again, the emphasis here is to say that whether you're using a heuristic or an algorithm with guarantees, the basic idea will, again, remain the same. Build a sketch structure that you can use to combine things together, and then build a hierarchy. Any questions?
The error is just depend on the level and not the partition.
Yes. Because of this property, by basically, since you're using only triangle inequality, you don't need much. Any partitioning will give you the triangle inequality property. It just might be, not that great.
Also in the string like random or arbitrary is not important.
But then you do pay a price for that, right? This error is quite high. So it's not coming for free. Obviously, you don't be a lot more clever. And in fact, I will talk next time about another way of doing clustering that has a very different perspective. That basically says that I can think of clustering as computing a singular value decomposition of a certain matrix. And then I will build core sets for that matrix property. And then use that to build mine. And that actually gives you much better bounds. You can actually get better bounds on the quality of the clustering using that approach. So this is using just sort of basic metric geometry of the data, which is not good enough. Those things are, if you have Euclidean data and you can do things like SVDs, you can do a lot better. So there's a whole line of work, and there's a paper in Stock this year, in fact, on a theory conference, a paper this year on how to get as much as you can use sort of this basic idea of using an SVD. So I ended early today. I didn't expect that. But I don't want to start the next topic now because it makes more sense to start. So just, if you have no more questions, I think, well, sadly for me, maybe good for you, we're done already. But I just want to remind you that next Tuesday we don't have class because I'm traveling. So we would reconvene next Thursday and we'll continue our discussion of clustering with streams using core sets and also maybe some distributed clustering. So in other words, what happens if you have individual nodes on, say, in the cloud, they have their own data and they want to cluster it jointly, but they don't want to send all the data separately. So the communication now is important. You don't want to spend a lot of communication, maybe very little bit. And so those of you who were in the communication complexity seminar last semester saw how it's, this is relevant to those questions. We'll see more about it. Okay. All right. So sorry about ending early, or not. And I'll see you next week.